Okay, so our job today is to figure out a formula, and there's going to actually be two of them for the probability of two events occurring together. Okay, so like again, we use the idea of rolling dice and flipping a coin or drawing cards. So it's like, what are the chances of it coming up a diamond and another diamond, or what's the chances of rolling heads and then heads again? Okay, so we can figure out the probability of each event and how do we work with them together. Well, today it's actually called the multiplication rule. This is called the multiplication rule here. Okay, and we don't have it yet, but we're gonna. So anytime you hear or you see and, it's going to be multiplication in probability. Okay, so this is going to be the multiplication rule today. But there's two of them, and you got to understand which is which. Okay. So this terminology here is called a conditional probability. So the probability of B given A, anytime you see the slash right here, that means given. So this is your condition. So we're trying to find the probability of B with the condition of A. Okay? And then I'll give you some examples of what that might be. You'll see that in a second. So again, conditional probability is the probability of an event, like this one, given that another event has already occurred. So this is the thing that has already occurred, or it's going to be, sometimes it's not how already occurred, but it's going to be like some sort of restriction. So when you do conditional probability, you got to think about this. This has happened, now calculate the probability of this. Or this is your restriction, now calculate the probability of the first one. So read it like back to front, okay? So let's do one here. So two cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. Assume that the king is not replaced. So you take the king out, you don't replace it. Now the question is, what are the chances that the second card you get is going to be a queen? Okay, so write this down for me. Probability that the second card is a queen, given that the first card is a king. So again, this is your restriction. So this has already occurred. Okay? So this is like the second thing has happened. What's the probability of the queen given that the king has been drawn? That's what I'm saying. So what is it? Give me a fraction. 4 out of 51. So there's 4 queens still left, but we're figuring out that the probability of that is based on the fact that the king is gone, so there's only 51 cards in, okay? Okay, you guys calculate this one. I'll give you a different problem. Probability of getting a king given that a king was drawn out of the deck. Tate, what do you say?
3 out of 51.
There you go. Okay, I'm going to tell you that anytime you see that you're going to have to think about it's going to be kind of a dependent situation. It's going to be a situation where you've got a condition placed on it. So. Okay, so let's do this problem. So it says a table shows the result of a study in which researchers examined a child's IQ and presence of a specific gene in the child. Find the probability that a child has a high IQ given that the child has the gene. Again, I want you to write this down. What's the probability of a child that has a high IQ given that the gene is present? So that's our condition, is that the gene is present. So that means we're only talking about picking out of that group. We're only talking about what are our chances of having a high IQ kid based on the fact that the gene is present. So what do you think this tells you? Does it tell you the numerator, denominator? Does it tell you anything? And so we're really picking out of a group of 72 people. So our chances of having a gene present, given that they, or high IQ given gene present, is that it's going to be 33 out of 72. So we're not even looking at the people where the gene is not present. Okay, do this. No condition. Calculate the probability of getting a high IQ with no condition. What do you guys think about that? And what do you think?
Well, 102 is the denominator.
Yep.
And then do you add the two high IQs together?
Well, that would be the 52 people right
never
here.
mind, I see that.
Okay. So
Yep.
yeah, you could have, but they also have it right there.
Yep.
Okay. Okay. Just want to point you out something because we're going to come back to this page here. That this would be less than 50% here. This would be more than half, more than 50%. So they're different, right? So if you calculate them out, I don't even care what they are. I just want you to know that this one and this one are not the same. So the condition placed on the probability changes the probability. Okay. So now, like I told you, there's going to be two formulas. And they're going to be based on whether the events are independent or dependent. So now we're going to talk about whether the events are independent or dependent. So independence, freedom, separation kind of. Well, in math, in statistics here, the occurrence of one of the events does not affect the probability of the occurrence of the other, means that the events are independent. One happening does not affect the probability of the other. So if I were to go back to this page, did this restriction affect the probability of this? Yeah, because they're different. Okay. So what would you say about these? These are independent or not? Not independent. Okay. So we would call them dependent events. So events that are not independent are dependent. And I'll go back to the other part here in a second. So if you can kind of look at a situation and think about if one affects the chances of the other, then you know that they would be dependent. If they did not affect it, they'd be independent. Now, if you had to kind of test something mathematically, this is what you would use as a test to show that they're independent or not. Okay? So if the probability of B given A is equal to the probability of B, then they would be independent events. So again, if these two are equal, so I'm saying that there's an equal sign there. Right? So if this probability is equal to this probability, then did this restriction change the fact that, or did it change the probability of B occurring? No. So if they're equal, independent. Okay? Or if the probability of B given, or probability of A given B is equal to the probability of A, then A and B would also be independent. Okay, so let's do this problem here. So we're going to say event A is it coming up heads on a flip of a coin. And we're going to say event B is rolling a 6 on a die. Okay? So what is the probability of A given B? What would be the probability of getting heads on a coin if I just rolled a 6 on the die? What's the probability of getting heads? If I jump up and down, or if I slide sideways, or I rolled a 6, it doesn't really matter what the probability of the coin coming up, right? So this is 1/2, and this is 1/2. So what does this have to do with this? Nothing. It does not affect the chances of it. So event A and event B are independent. Okay. So again, that's what we're testing right here, right? Does this condition affect the probability of the first event? And really, in our mind, we know that it doesn't. So we know they're independent events. Okay. Now, I'm not going to make you turn to this page. I'm just going to give you one problem that was on there that I can remember. Okay. So let's say that event C is getting a speeding ticket. Let's say event D is driving 92 miles per hour. Is the chances of getting a speeding ticket different with this than without? Like, give me your estimate of driving down the interstate and getting a speeding ticket. You ever got a speeding ticket, Tate? Anybody got a speeding ticket? Yeah? How fast were you going?
Like 15 over.
Okay. So our chances of getting a speeding ticket aren't great. Do you think our chances of getting a speeding ticket are greater if we have this going on? Yeah. So then these events are dependent. So if one affects the other, they're dependent. Okay? That should make sense. So this is going to be our formula for independent events. This is going to be our formula that doesn't really say it for dependent events. And we know means what? Multiplication. So we're going to do some multiplying, and the first one is really easy. The probability of A and B is the probability, oh, I don't want that one. I want to do this one. This is the easy one here. The independent one. So the probability of A and B is the probability of A times the probability of B. Multiply them out. The probability, if they're dependent, is the probability of A, so it starts the same way, times the probability of B given A. So I want you to understand, like, if you got different letters other than A and B, how would it work? Well, the probability of Q and M would be the probability of Q times the probability of M given that Q has occurred. Okay? And now they're saying that it could extend for, like, you could do the same thing whether it's like for one event or there's 2 or 3 or 4 if there's more than 2. Okay, so let's go back to the page where we had the gene present and high IQ kids, and I'm going to give you a problem. The problem was on the page, but I'm going to write it down. So I want you to calculate, and we'll think about it. What's the probability of, what does it say on the page? Is it high IQ first and gene present, or other way around? High IQ?
Gene present.
Gene present, okay. So what's the probability of gene present and a high IQ kid. It would work the same either way. I'm just doing it this way because that's what I had written down. Okay, so here's the question. Do I use the independent rule or the dependent rule? What did we say was true about that and that? These probabilities were different. So what does that mean about these events? They're dependent. Okay? Did this restriction change the fact of this? Yeah, this was like, if we wanted to figure out, it's a little bit less than 50%, maybe 48, 49%, and this would be a little bit more than 50%, maybe about 51%. So the probabilities are different, so then these are dependent events. So you have to use this formula. Probability of gene present times what? I'm not going to say it. I'm waiting for at least the wrong answer. So is it going to be gene given high IQ, or is there going to be high IQ given gene? High IQ given gene present. And I'm abbreviating here a little bit. Okay, so there's our, what's that symbol mean? That means given, right? So again, probability of A and B is the probability of the first one times the probability of the second one, given that the first has occurred. So that's how you organize it, right? So it's going to be ABA, gene HQ gene, in terms of organizing it, okay? So what's the probability that the gene is present with no restriction? There's the probability of finding somebody in here that has the gene part of their makeup out of 102, no restriction, right? Times the probability of having high IQ with this restriction, so it would be, what fraction here? 33 out of 72. Now, I don't need you to reduce anything, but one thing when you're multiplying fractions is you have factors in the top and the bottom that are the same. You could simplify this really quickly to this, at least. And it would simplify further, but I'm not going to worry about that. Now here's the deal. I made you do way more work than you had to, just because I wanted to show you the formula worked. But if I went to this 102 people, what's the chances that I picked a person that had a gene present and had a high IQ without doing any of this stuff right here? It's going to be 33 out of 102, isn't it? So I wanted to show you that the formula worked because that's what we got. Okay. So let's try another one that doesn't refer to this. Okay, so we're getting close here, right? So two cards are selected without replacing the first card from a standard deck. Find the probability of getting a king, and then selecting a queen. So write that down. Probability of getting a king and then a queen. Okay, so here's the deal. Anytime you have this in the problem, it's going to mean something. Okay, now you tell me what you think it's going to mean. If I take a card out of the deck, does that change the probability of the next draw? So that means that this is going to tell you we have what type of situation? Dependent. So we're going to use our dependent formula here, which would be the probability of drawing a king first times the probability of drawing a queen, given that we drew that first king. So this is what? No restriction. 4 out of 52, which would be 1 out of 13 if you wanted to simplify it, but we don't need to do that. Or should we? Should we do that? No? Okay. Okay, now what's the probability of drawing a queen, given that I drew the king? 4 out of 51. So your probability would be 16 out of something. I got it written down here somewhere. Out of 2652. So not a very likely outcome. Like less than 1%. It's kind of a random event anyhow. Okay. Okay, now I want you to calculate this. Probability of drawing a king and then a second king. Write the formula down. Maybe anybody tell me what it would be. What would you write down? Probability of a king times the probability of king given that I drew a king, right? So the chances of drawing the second king is 3 out of 51. Now think about it. Do you think that your chances of drawing a king and a queen are going to be the same as drawing a king and then drawing the second king? That second king is going to be a little tougher, so you have 12 out of 26, 52 instead of 16 out of 62, 2,652 chances. Okay, so that should seem reasonable. Okay, let's do this one. So a coin is tossed and a die is rolled. What kind of events are those? They're simply well, there wouldn't be simple events because there really could be 2 things here and 2 things here, but they would be independent events. Okay. Find the probability of getting heads on the first and rolling a 6. So the formula would be probability of rolling heads times independent formula P of 6. They're not dependent, so we don't need to worry about that given stuff. So this would be probability of rolling heads. 1/2. Probability of rolling a 6, 1/6. So that would be 1/12. Now, if you listed the sample space, that should make sense. So there's more than one way of calculating probabilities. We're working on the formula, but you could have listed the sample space. And how many of them end up with heads and a 6? 1 out of 12. So there, you could list the sample space and calculate it that way too. So we're just giving you more ammunition here. Anybody got a question here? Okay. We're getting close. All right, so what's the probability that a particular knee surgery, or the probability that a particular knee surgery is successful is 85%. I had some people, when I went through this, they said they didn't like that. They didn't like those odds. They wanted a better result of knee surgeries. But so now the question is, or the thing they want us to find is, find the probability that 3 knee surgeries would be successful. So write this down. Probability that the first one is successful and the second one is successful. Isn't that kind of what we're talking about? We want the first one successful, and we want the second one successful, and we want the third one successful. Now, I'm going to tell you that I'm making the assumption that one surgery's success is independent of the others. Like, how one went isn't going to affect the chances of the other. I'm just going to say that I think this is independent. Okay? So that means that we're going to take the probability of success times itself 3 times. So that's going to be 0.85 times 0.85 times 0.85. And that's about 61%. Can you tell me like a little bit more accurately what it is? I think it's 61. I needed your help, but no, we're not going to do that. So I got it now. Okay. Thanks for the help, Tate. Okay. All right. So the next one, find the probability that none are successful. So we want the first surgery to be not successful, and the second surgery to be not successful, and the third to be not successful. So what's this probability here? 0.15. So then this guy is going to be 0.15 times 0.15 times 0.15, or 0.15 cubed. So that's going to be a really small percentage. So that is less than 1%. So we're going to say 0.003. So we're going to reinforce this a little bit more on Wednesday. I'm going to go through this, kind of discuss this a little bit more, and then hopefully it'll make more sense as far as why this happens. Okay. So now, let me write this down. I don't want you to write this down, okay? But I want to show you something. Okay, so you could have a situation where all 3 surgeries are successful. You could have it where the first 2 are and the third one isn't. You could have it where the first and the third are and the second one isn't. Or you could have the first one and not the next 2. Or you could have the first one not and the second 2 be successful, the first one not and one of the final 2 not, or none of them successful. Okay? So with that in mind, is the chances of this the chances of this? Did we learn that they are on the last page, or we learned that they weren't the same, right? So these are not equally likely outcomes. So you can't use like that heads and tails idea. Are these equally likely? Yeah, so the probability of heads is 1 out of 2. But you have to know the things that you list are equally likely to use that formula, 1 out of 2. You don't know they're equally likely, so we can't do that when we're calculating probabilities here. So at least 1 of 3 successful means we need to find this probability and this one, right? Aren't they at least 1 successful here? And that one, and that one, and that one, and that one, or something else. How could we find the chances of all of this happening? As easy as possible. Nope, not necessarily. Let me ask you this. What's the probability of rolling a 5 or greater on a die without calculating each of those? Or let's go 5 or less. What's the chances of rolling a 5 or less without calculating all those? Calculate the probability of getting 6. Calculate the probability of its complement. Isn't a 5 or less and this a complementary event? So wouldn't it be easier to find this and then subtract 1 from it to find the probability of it? So I'm saying find the probability of this, which you know, and then subtract it from 1. So write this down. Probability of at least 1 successful. What's the opposite of at least 1 surgery going well? Is 2 going well? At least 1? Yep. Is all 3 of them going well? At least 1? So what's the only thing? None of them going well, which is this guy here. So this guy and none successful are complementary events. And we know this. So now we know the chances of at least 1 going well. Okay, there's the idea of using the complement to really make it easier. Okay, so if it seems really confusing, try finding the complement. And that's hard, right? You gotta think, at least 1 means 1 or more. Well, what's the opposite of 1 or more going well? None going well, okay? So, again, you can try a couple. You'll have some time on Monday